Thank you, Simone, for the nice introduction. Yes, I want also to thank you all the organizers for inviting me to have this talk today. I will present on the application of the two-level method for LPBF simulations, and this work was done in collaboration with my colleague Alex Vighery from the Gran Sasso Science Institute and Alessandro Reali and Ferdinando Ricchio from the University of Pavia. So the outlook of my talk is organized as follows. I will start with a brief introduction on the main computational challenges that we have to face in laser power bed fusion and motivations to introduce a novel methodology to treat this kind of simulations. The two-level method that we proposed was first designed to be a method in space and is rather flexible. So we have implemented both for high fidelity model simulation and also part scale model simulation. And in the second part of the talk, I will present the results that we have obtained adopting this approach also for time-space simulations. And finally, draw the main conclusion and further outlook of the research. So as we all know, simulating LPBF processes is not an easy task due to a lot of peculiar features of this technology, and in particular, the large scale range in both space and time that make this kind of process naturally a multi-scale problem. Moreover, we have to deal with complex physical phenomena and also complex geometries that are usually used in the part that we produce with LPBF. So due to this problem complexity, we need to choose a priori the resolution scale for our code. And this is done maybe choosing the quantity of interest that we are looking at with our numerical simulations. In particular, in this work, we focus on a melt pool analysis, which we call high fidelity simulation, and a lower resolution scale, that is the part scale analysis. The first one is used to predict melt pool morphology and cooling rates in the neighborhood of the melt pool, and is characterized by the simulation of few laser strokes, including powder and phase change into the physical model. Whereas the part scale model is used to predict part scale deflection, residual heat and stresses in the final component, and therefore is rather a more approximate model that where we employ constant heat source and we neglect the latent heat. So the motivation that brings us to adopt, to develop a two-level method is that we want to somehow keep together the local scale feature and the global scale feature in the same numerical framework. And in particular, we want a method that is flexible and avoid continuous refinement and coarsening of the whole domain. Also, which allows a full scale separation such that we introduce a further flexibility compared to standard FEM approaches. And we are able to potentially even use different physical models in the local scale and in the global one. But now let's have a look more in detail on the characteristic of this two-level approach. The idea is to address a special multi-scale problem with two separate meshes on the global domain and on a local domain, which is resolved by means of a finer mesh. In both problems, the global problem, the coarse global problem, and the local one, we solve the heat transfer diffusion problem. The global solution is coupled to the local one, imposing the temperature solution of the global problem on the boundaries of the local one. Whereas the local solution is coupled with the global problem by means of this d-1 term, which is introduced in the strong form of the problem, and where we basically impose the continuity of the heat fluxes at the boundary of the local domain omega minus. In this sense, this method can be seen as a generalization of the FAP boundary method, first proposed by Mauri in 2001 and further developed by Bertoluzza in 2011. With two important distinctions: the two-level method, the boundary of the two-level method are true physical boundaries for the problem, And we do not require that the boundary of the local domain do not intersect the boundary of the global domain. In any case, for further detail on the mathematical implementation of this framework, I will refer to two recent articles published by my colleague Alex Viguerie last year. What we have done was to apply this numerical framework, this methodology, to laser power bed fusion problems. So the first one is employs a high fidelity thermal model, where at the local problem, we model the laser heat source by means of a Gaussian source model, and we impose convection and radiation boundary condition on the upper surface. We also consider a temperature-based phase change as proposed by Celentano in 1994. And again, the coupling is done imposing the temperature, the continuity of the temperature at the boundary, lateral and bottom boundary of the local domain. Instead, for the global problem, we consider a constant heat source and only convection boundary condition on the upper surface, whereas we fix the temperature at the bottom of the base plate and we impose adiabatic boundary condition on the lateral surfaces. But since the method is rather flexible in terms of physical model, we have also introduced a part-scale thermal model, where in this case, at the local size, the local problem, we consider a homogeneous model, including powder, and again, convection and radiation boundary conditions. Whereas in the global problem, we only consider convection condition on the upper surface, and we model the conduction through the powder with heat flux boundary condition on the lateral surfaces of the powder bed. We have modeled the part-scale activation scheme using a rather simple activation procedure. We agglomerate 20 powder layers at each activation step for a total size of 1 millimeter. And we perform first a heating time step with a time step size of 80 microseconds, where a uniform heat source is applied on the newly activated layer powder. Then we perform 3 cooling time steps with a time step size of 3 seconds, where the part is cooled down. And finally, 1 layer deposition step, where we basically allow the residual heat to diffuse into the new layer of powder. We have tried to validate this implementation, this model, comparing with results presented in the literature, and in particular by measurements of the activation temperature of the new layer performed by Williams and co-authors in 2019 on the LPBF process of a cylinder 60 millimeter high made of stainless steel 316L material. They choose an interlayer cooling time of 11 seconds, and they measure at each layer the activation temperature. As we can see with the proposed two-level approach, we are able to closely capture these experimental results. So of course, this work doesn't mean that the method and its implementation is completed, but at least we are confident that we are going in the right direction. But now let's go back to the high fidelity model and try to push a little bit further the constraint of the two-level method, exploiting its great flexibility, such that we develop a spatiotemporal approach. Before starting, we had a little literature research, and we have found that there is not so much research going on in this moment on this kind of approaches. We have found the multi-rate model proposed by Hodge in 2021, where the model considers 2 different sets of degrees of freedom, a fast set of dots and a slow one that has to be continuously updated by means of a predictor corrector scheme in order to correctly follow the laser movements. Another method that we have found is the Telogenius time stepping proposed by Solden and Mergheim in 2019. They employ a domain decomposition approach together with a discontinuous Galerkin method that can be adapted in time using a merge and split scheme. Finally, it was very recently published the multi-time stepping method by Cheng and Wagner, where a substructuring domain decomposition is employed together with the Dirichlet-Robin iteration approach, leading to significant reduction of computational cost and conditional stability together with a rapid convergence rate. So what we have done is to take the multi-rate method proposed by Hodge and combine together with the two-level framework. This is, say, an overview of the implementation that we have done. At the beginning, we solve the classical two-level coupling scheme. So we first solve the global problem, then the local problem in the local domain, and we iterate the solution until we reach convergence. At this point, we compute a predictor step where we compute the global solution only at the time step tn plus delta t. And at this point, we start to solve the micro time steps at the local problem. And in this case, the coupling is made only in one direction with respect to a linearly interpolated global solution between the previously computed global solution and the predicted one. Once we have completed the k macro time steps, we again solve the two-level coupling problem in the one that we call the correction step in order to obtain an updated global solution, such that we can now start again the macro time step scheme. We have first tested this implementation on a two-dimensional problem where a laser source travels on the upper surface of the square domain, and the top layer is our local problem domain, which is discretized with a much finer mesh compared to the coarse one. So the goal of this convergence study is to observe the ability of the proposed spatiotemporal implementation to capture the complex nonlinear behavior of this problem, and also to quantify the rate of convergence with respect to the reference solution that in this case is the classical, let's say, two-level solution. So as you can see in this first convergence plot, the error in the L2 norm quite rapidly converge when we decrease the macro time step size as expected. We can also notice these oscillations in the error distribution that are due to this predictor corrector implementation. But in any case, the maximum error is controlled such that we can really simply decreasing the macro time step size to achieve a very good convergence. Also, this effect can be observed in the temperature distribution over time. This is the temperature evolution at the mid-path point. And as we can see, for very large macro time steps, we have oscillation in the temperature profile that immediately disappear when we decrease the macro time steps. So the takeaway message of this slide is that we can control with this implementation, this approach, the error in our solution, simply reducing the macro time step size. So the methodology allows to choose between an optimal trade-off of computational time and accuracy. We have also computed a three-dimensional benchmark. In this case, we have computed also a reference solution obtained by standard finite element method with a very fine discretization and time step size. We have compared the reference solution, the temperature plot of the reference solution with respect to the result obtained with the classical two-level method only in space, and the new implementation of the two-level method in space and time. As we can see, both temperature profile closely recover the reference solution. The overall speed up that we obtain with the space-time implementation is up to 20% with respect to the two-level implementation in space only. But the global solution time is reduced by a factor of 2, choosing a delta t, which is a macro time step size delta t, which is 4 times larger than the micro time step size. So in this sense, we can expect that extending the global domain to simulate more complex scan path, we can achieve this kind of speed up factor using a space-time implementation. So this was not done so far because computer reference solution already for this simple problem was quite demanding in terms of both memory and computational time. So this leads me to the conclusion of my talk. The two-level method that I have described allows to an easy separation between a local fast scale and a global slow scale. The flexibility of this formulation allows also to adopt different physical models in the local and the global scale. And it can be easily extended to a spatiotemporal formulation, which does not require a continuous update of the mesh, since this is automatically handled by the two-level formulation. Moreover, the structured grid of the two-level calls for massive parallelization. Therefore, in the future, we hope to be able to parallelize this implementation such that we can easily achieve the much larger simulations. And also we plan to extend this kind of approach to thermomechanical problems at both high fidelity and part scale size. This is not trivial also from a theoretical point of view, but we are currently working on this issue, and we are relatively optimistic about this possibility. So thank you very much for your attention, and I'm open for discussion. Thank you.
Thank you very much, Massimo, for the interesting talk and also for restoring somehow the time schedule. So, okay, Ernst has a question, so please.
Yeah, Massimo, thank you very much for this very nice talk. What is it a problem where you turn around the laser track? So at the end, meaning that when you go back in the hatching, then you're coming to areas which are not, well, in a sense, homogenized in the temperature, and you need to refine, or you need to have your second, your fine layer again in these parts. What do you do in these situations?
Yeah, we have tried to move around the laser. And the solution that we have found is that for a few adjacent layers, you have the melt pool instabilities and rather high temperature gradients. And in this case, we select the local domain large enough to take into account of this number of layers. Then at a certain point, the temperature gradients decrease and it somehow stabilize, the same as we can see for the tail of the temperature solution. Also, yeah, here. So basically, we have this effect also in the other direction. Mm-hmm. And at this point, the global coarse discretization is able to capture this effect. So, of course, the local domain has to be large enough to capture this, but let's say compared to the size of even a small portion of powder bed, this is still much smaller.
Mm-hmm. Yeah, thank you.
You're welcome.
Any other question from the audience? While waiting for other questions, okay, Paul, please.
Okay, maybe this is naive and maybe I didn't listen well enough. So your method is essentially, is that like a domain decomposition where in the one domain you have a more dense discretization and you put a little bit more complex physics models there, and in the other part you have, let's say, a more coarse mesh and more simplified physics?
Yeah.
Or is that the wrong interpretation?
You can see also in this way say the core of the numerical methodology is that you exchange this information at the boundary. In the original formulation that is published in the the two articles by Alex. The exchange of information is done on a volume integral. In this case, it was too expensive from a computational point of view to treat this kind of problems. Therefore, we decided to pass to couple the information between the global and the local scale only at the boundaries. And we have seen that the result is still rather stable, and despite the strong nonlinearity in the material model, the accuracy is kept by the method.
So let's say the domain where you have the, let's say the final level,
yeah,
is only occupied by that kind of discretization. It's not that the
no. Okay, now I understood. Yes, no. The global domain also include. Let me go back to the right slide. Yeah, sorry. Now I got your question. So this omega minus is also in the global problem. So we solve the global problem on the entire omega.
Okay.
Plus, we have a separate mesh on omega minus. So we solve the local problem on this mesh. And we exchange information at the boundary between the two. So it's not like that the global problem is solved only on the subdomain omega plus, but it's solved everywhere on omega.
Okay.
So in this sense, it's not a domain decomposition approach.
So let's say from the viewpoint of the global problem, the boundary to the omega minus is like a distributed heat source or something along a line, or can we say so?
Yes, exactly. Yeah.
Okay.
Yeah. Is you have the heat flux here, and then you have to integrate over this boundary, which is immersed into the global domain, and then in this way you exchange information.
Okay.
In this way that we have implemented right now.
Okay, thanks a lot.
Okay, Shanmugam, do you have a question for Massimo?
Yeah, just a follow-up question. Interesting talk. I was just wondering whether the time scale used for the two different domains are the same. Do you have, because they have natural built-in time scale, isn't it? Or they are different?
Well, so in the original implementation of the method, so only as a spatial multi-scale method, the time scale that we use, so the time step size for the global problem and the local one is the same. Instead, in the novel formulation that I have presented, we use a multi-rate approach. So we have a lowercase delta t, which is a time step size for the local problem, and uppercase delta t, which is instead the time step size for the global problem. So we have two different time scale in the global and in the local problem.
But does it still take care of the kind of temperature gradients we expect in a physical process? Because for computational convenience, we split this into two domains and solve it. But then the physical problem has a natural inbit time scale, and the heat transfer occurs.
Yes. So for the local problem, you have a much smaller intrinsic time scale that you have to resolve with a small lowercase delta t. The global problem instead is used basically to capture the tail of the temperature distribution when the gradient is much lower.
Okay. Yeah.
So in this case, we take advantage of this fact to use a larger delta t. So here. So the local problem allows us to resolve this part with high temperature gradients. And of course, if the local domain is too small, then it does not converge. We have problem of instabilities because then we are trying to capture with a coarse time and space resolution a problem which has high gradients, and then the solution is broken. So the local problem has to be large enough related to the question of Professor Rank before. No? So when we turn the laser, also we have this kind of instability and nonlinearities occurring in the remelted area. So we have to adapt our local domain size. It always depends what we want to capture. No? So it's the
yeah.
size.
Yeah, thank you. I got it. Thanks.
You're welcome.